The last thing we'll do for this chapter is look at what these solutions look like. So everything we talked about has been purely kind of mathematical. But the nice thing about this is that the solutions, we can visualize them and see what they look like. And so what I've got here is an Excel sheet where I've put in these solutions. Right, so our equation that we had before, I've only taken n up to 4, but of course we can go higher than this. And then we have our coefficients here, amplitude, an. We have our frequency, omega n. That was the combination of some constants here. So it's n times pi times I1 here is our v value. So it's the speed of the wave, 5 centimeters per second. And then I took L to be 10 centimeters. And so this is our representation of the string. So what we have right now currently is an equals 1 and 0 for everything else. So a1 equals 1. And so this is a representation of sort of the simplest normal mode if we only have the n equals 1 part of the string vibrating. And what I have down here is I can change the time. So this is where it looks like at time equals 0. If I increase this to, say, 0.25 seconds, we can see the amplitude has started to decrease. If we go to half a second, it's gone down even more. If we go to 3/4 of a second, it's gone down even more. If we go to 1 second, the string has reached the middle. If we go 1.25 seconds, it starts to go below. 1.5 seconds, it goes down underneath. 1.75, it gets even further down. If we go to 2 seconds, it's down at the bottom. And we can keep going here, right? If we did 2.25 seconds, it would continue to come back up. And this is going to repeat. It's going to go up and down and up and down. And this is sort of the lowest normal mode. Now, if we go back to time equals 0, if I switch the amplitudes here, if I put everything 0, this is our trivial solution, right? The string just stays still. But if I make 1, or n equals 2, the amplitude equal to 1, this is our second normal mode. And we can do the same thing. We can change our time here. So if we have 0.25 seconds, it starts to decrease on both sides, comes down on the left side and up on the right side. Go to half a second, we see it's already reached the middle there, right? So the second normal mode moves faster. 0.75 seconds, starts going the opposite direction. 1 second, we've reached sort of the opposite amplitude. And we can keep doing this here. And again, this is going to repeat in a pattern. And so this is our second normal mode. Looks like that. In our third normal mode, like I showed, is sort of like this. Oh, if we start at 0, we can see that it'll, decreases like this as we change the time. So it's kind of waving up and down. Now, and just for completeness sake, we'll look at the fourth normal mode. N equals 4, we get this where we have multiple, now multiple waves represented here. And each of these represents more energy in the string. It's vibrating, it has to move around faster to keep it up. Now, there's nothing that prevents us from having only one normal mode at a time. So we could look at something where, say, we have contribution from all 4 of these normal modes. Say equal contributions from all 4. And so we get an initial condition that looks something like this. And the string is going to vibrate, but not necessarily in a completely predictable manner, right? And so we see this sort of combination. And we get something that might look like we've started our string in a weird way, or this vibrating string. But this will eventually repeat if we keep going. And so we can kind of see the displacement kind of moving along the string. And we can, one fun thing you can do with this is you can make animated GIFs out of it, right, to kind of show how this string is moving as a function of time. And so this is just looking at, this is a solution to how strings actually vibrate in real life. They follow this wave equation. And so the reason this is useful is a lot of these mathematical techniques we've talked about, where we end up getting quantization as we solve differential equations, where we have boundary conditions that matter, separating variables into different parts. These are all going to show up. These ideas are going to show up again and again as we talk about quantum wave equations as well. And so, but the nice thing here is that we have an actual physical thing we can visualize. This is what a string would actually look like. It would be displaced by some amplitude in centimeters, and when you pluck a guitar string, it follows this equation, which is, I think, one of the neatest things about this. And so this is something you'll get to play with on your homework assignment as well, looking at some specific scenarios that I'll ask you to look at.